Hi, I'm Tom Linker.
I'm Roger Martinez, and this is our photocopier.
So the way our photocopier works is it goes in and it scans a 3 by 3 grid of 2.5 by 2.5 centimeter squares. It detects if the square is filled using the LabVIEW color sensor, and then it records its information to its internal computer.
And it completes the circle by turning around, going to a new sheet of paper, and reproducing what it sees. So it senses its environment, and then it goes and has its own response. And that's how that works.
And now let's see it working in action. First we will show you the robot in read-only mode, where it goes over the grid, it scans the image, and reproduces the image of a set of LEDs on the LabVIEW front VI panel. As you can see, it goes over each row, uses the LabVIEW color sensor to detect whether the square is filled, pivots forward, and then scans the next row. Now we have the robot doing a standard copy and print, where it will go over each row of the grid and scan to detect if the grid is full. As you can see, it's doing its standard pivoting forward, pivoting backward to make sure that we hit every row on the grid. Once it's finished hitting all the rows, it goes forward, backs up, turns around, and then goes forward to a blank sheet of paper to recreate the image. As you see, we can't get it quite the same size simply because our pen isn't big enough, but we are successful in recreating the image. One of the main issues you can see in this sped up version of a print and copy is that the robot is very sensitive to initial conditions, and if it starts slightly offset, it will miss some parts of the image. As you can see in this, it will miss the middle row and fail to reproduce that row, while it still successfully reproduces the other row. Next, I will have Roger walk you through the LabVIEW code that makes all this work possible.
Let's take a tour of the code that makes the robot run. Our LabVIEW code works in just a few easy steps that can be repeated over and over again. Let's start off by talking about the sub-VI that allows the robot to sense its environment. This sub-VI runs on a for loop that iterates n equals 3 times, once for every time it stops to read data from the three 2.5 centimeter by 2.5 centimeter squares on the paper that make up a column. Both motors move together 53 degrees forward at 15% power, and the car stops and uses the color sensor to read the color on the paper. The colors are checked to see if they are black using the comparison tool. If the color is black, then a Boolean true is output, otherwise a Boolean false is output. These values are then passed through the Boolean to numeric converter, which allows us to store data in terms of ones and zeros. These values are sent into an array that was initiated out of the loop, and that's it. The sub-VI is used again in the program to capture data of each new column. We primarily make use of the flat sequence so the operations we want to execute happen in sequential order. So the robot begins scanning the grid by using the acquired data sub-VI I just mentioned. Once it's done, the data is tunneled to the next frame, where the array is read with an index array icon. Then every element of the array is checked to see if its value is the number 1, meaning that the robot detected a black square on the grid. If the value is 1, then the corresponding LED will light up on the front panel of the VI. Of course, this is only for the first column, but it will repeat after scanning each column of the grid, such that the front panel LED grid will reflect the same pattern that the robot sensed. Once the robot finished scanning a column, it is ready to reposition itself to read the next column. This is done by running through the rest of the operations on this image. The car runs both motors in reverse at 15% power for 159 degrees. Then the car pivots back by running one motor, motor A, back 400 degrees. Then the car creeps forward by moving both motors 45 degrees. Now it's ready to pivot back towards the grid. The fourth frame is simply run backwards, where motor A runs forward 400 degrees. At this point, the car is facing the grid again, but it has come up short from the starting position. To account for this discrepancy, the second to last frame we see here makes the car scoot forward just 15 degrees so that it's repositioned at the beginning of the second column. All operations that the car does happen at 15% power. We chose this relatively low value because more power could cause the car to lurch violently, which in turn puts it off course. That concludes the realigning maneuver so that the car executes the acquired data sub-VI again and repeats it again for the last column as well. Let's fast forward a bit and see what the robot does once it finishes scanning the 3x3 grid. If it is connected to the computer, it will report back which LEDs light up. Then it will alternate supplying power to both motors to make it rotate 180 degrees. Then it drives over to a clean sheet of paper so it can print what it saw with the right data sub-VI. This sub-VI works pretty simply. It takes in the array values acquired from the scan and processes them in a case structure. The car moves to each pixel, and if the array value is 1, then it puts a dot with the marker it carries. If it sees a 0, then it won't put a dot down. Just like before, once it finishes a row, it needs to back up and do a few repositioning maneuvers to be aligned with the next column. This can be seen here in this image. And that's it. Once it finishes printing the last row, the program shuts down and the scan and print process is complete.
As you can see, the car was very sensitive to the initial conditions. One way we could have improved upon this was by creating two VIs and having them read and write files so you could reset the car twice manually and not have to worry about doing it in one shot.
Another alternative would have been to have a more stationary design where instead of a car, it's just a motor scanning over the grid while it's going on a rail so that we don't have to worry about it going off course. And this would allow us to go over a larger region, a larger grid without going offset, just like we saw in the fail video.
But at the same time, at least in the color detect mode, the sensor had trouble detecting squares any larger than the size we were using, so we'd have to figure out a new detecting mode in order to detect smaller squares. But in the end, our project was very successful in producing the image, and thank you for watching.